Alright, so now that we know what convolution is, and again it is sliding a filter over a signal to create a new signal. Yeah. But why Covnets? We've seen fully connected layers. Why don't we use that for image recognition, for example? Well, it's quite simple. Assume you have a color image here, an image 1000 pixels, 1000 by 1000 pixels, and you have, of course, a color image, so you have your RGB. Yeah. So in this case, you have 1000 by 1000 by 3 features. Every pixel is a feature. So this is 3 megapixel. Yeah. These are your inputs. So basically what you have here, you have your x1, x2, all the way down to x 3 million. Yeah. And assume we have now a hidden layer of 1000 units. Yeah. Remember that all of these will be in a fully connected layer. All of these are connected to each other. So each of these hidden layer neurons will see all the x1 to the x3 million. Remember that our so sees whole input, and so do these other 999. And remember that we have to use W transpose X. X in our case is a 3 million times 1 vector. The W that connects these two must have 3 million columns, because these two need to be the same. Yeah. And on the other hand, you have 1000. Right? So how many parameters do you have? Well, here is 3 billion parameters. So you see that the number of parameters is going quickly through the roof. Yeah, and that's why fully connected dense layers are not very suitable for things like image recognition, especially when you go to high resolution. Now that's not the only issue. Yeah? There's another issue. The other issue is that in order to feed this picture into your dense neural network, you gotta flatten the picture. And you gotta make a one-dimensional vector. And if you make a one-dimensional vector, you lose your spatial information. Yeah. So this is a second issue. So first issue is way too many parameters, and second issue is you lose your spatial information. And Covnets basically solve two issues.